Okay, so we move on to question 7, where we need to graphically find the convolution between two signals, both of which contain only impulses. So we've got one signal xt, which has an impulse at location 0 and 1. And then we've got another signal ht, which has an impulse of strength 2 at 0. It has an impulse of unit strength but in the minus direction at t equal to 1, and another impulse of negative 1 strength at minus 1. So we need to find the convolution of these two signals. This is ht and this is xt. So of course we'll follow the same process, and the question requires us to solve this graphically, right? So we'll follow the same process as we followed before. We'll convert them both into tau domain. Out of the two, I find this one easier to flip and shift. So I'm going to write, so if this is x tau, that means this is x of minus tau. This edge is here at t equal to 0, because this, if we were to write this in terms of t minus tau, this means at t equal to 0, this leading edge, this impulse is situated here, right? That means in general, I could say this is t and this is at t minus 1. So I've got x tau and I've got h tau. So we're going to take different cases like we usually do and find the convolution. Right? So say in the first case, this t has not yet reached minus 1, right? Tau equal to minus 1. So for t less than minus 1, we can say that yt, which is the convolution between the two, is 0, right? Now, it's very obvious by looking at these signals that the only possibility of there even being an overlap is only at integral multiples of tau, right? So there can be a overlap at tau equal to minus 1, 0, tau equal to 1, and tau equal to 2. That's it. There's no other possibility of overlap. So instead of writing it as range of t, we can also write it as exact value of t. So say for t equal to minus 1, what is the scenario? This is h tau, right? 1, 0, and minus 1. And for t equal to minus 1 means our signal x tau minus xt minus tau is situated here, right? This is t and this is t minus 1. So in this case, we can clearly see that only this impulse, these two impulses are overlapping. That means in terms of integration, of course, I'll keep the limit as minus infinity to plus infinity, but we know that only these two impulses are being multiplied. So let us write these two impulses. So the one in blue, which is coming from x t minus tau. How do I write that impulse? That impulse can be written as delta situated at t, right? So it can be written as delta tau minus t. The other impulse, the one coming from h tau, how can that be written? It has a strength minus 1, right? So I can take this minus 1 outside actually. And how do I define this in terms of tau? It is delta tau plus 1, right? So a delta function in tau domain, but situated at minus 1. This is how that can be written. And its strength being minus 1, I've taken it outside already, right? So this is the product that we need to find. Now we can clearly see that this particular term is 0 everywhere else other than tau equal to minus 1. That means the only possibility for this product to be non-zero is at tau equal to minus 1. So at tau equal to minus 1, if I plug in tau equal to minus 1 here, I can actually, for that infinitesimally small duration, consider it to be a constant and take it out. That means I could have written this as delta minus 1 minus t integration minus infinity to plus infinity delta tau plus 1 d tau. Now we already know that this term is equal to 1, right? So all we've got is minus delta minus 1 minus t. Okay, and how does this impulse look like? It has a strength minus 1, and can we say where it is situated? You remember from the compound operation of time scaling, you first do shifting by minus 1, right? So you would have shifted an impulse here, then you would have reflected it, that means it came here at minus 1, and then it has a strength minus 1. That means it's not a positive impulse, it's a negative impulse situated at minus 1, right? So that's also the case that we were talking about for t equal to minus 1. So we have at t equal to minus 1, we will have an impulse of minus 1 strength located at minus 1. Okay. Next case is when our x t minus tau progresses further inside. The scene is something like this. So progressing 1 unit further, that means it has reached here. So this is t and this is t minus 1, right? So this is 0, 1 and minus 1. So what is this condition? This is when t is equal to 0. At this location, what is the overlap? There is an overlap between these two impulses as well as the one at tau equal to minus 1, right? So let us write both. So for the first case, we can say that, how do we define these two impulses? These are like saying this one is situated at t minus 1. So I can say this is delta tau minus t minus 1. So tau minus t plus 1. And the other one minus delta tau plus 1 d tau. This is this product that I've written. Next term, the overlap of these signals, these impulses. That means I can write this as integration minus infinity to plus infinity delta tau minus t. That means the one in blue, that is a impulse in tau domain but located at t, and the other one is simply delta tau d tau but having a strength 2. Okay, so when we solve this, let's solve the first one. We know that the product will be non-zero only at tau equal to minus 1. So I plug in tau equal to minus 1 here, minus 1 plus 1 disappears, and as a result I get delta minus t, minus delta minus t, integration minus infinity to plus infinity delta tau plus 1 d tau, which is equal to 1, so I'm not writing it, plus the second term. Where would this lead us? It would say 2. Again, this product is non-zero only at tau equal to 0, and I plug in tau equal to 0 here. I can actually take it out for that infinitesimally small duration of time, which is tau equal to 0. And there I could say, if I plug in tau equal to 0, this is like saying delta of minus t, integration minus infinity delta tau d tau, which is equal to 1. So I'm going to erase this, right? So minus delta minus t plus 2 delta minus t is equal to delta minus t. And because we know the property of delta function, delta t and delta minus t, because it's situated at 0, right? So if you take it or its reflection, it doesn't matter. So this is like saying this is same as delta t. Okay, so for at t equal to 0, we would have one impulse of unit strength. Next case, so now this xt minus tau is moving further. Now what happens? Now our xt minus tau has reached here. So this is t minus 1. At this point, you notice an overlap in this region. So there are two sets of impulses which are overlapping. So now I can write yt as integration minus infinity to plus infinity. Let me write the first set of impulses. And this can be written as, so the one in blue can be written as delta tau minus t minus 1. That means delta tau minus t plus 1. The second one can be written as 2 delta tau d tau. Taking 2 out, we know that this product will be non-zero only at tau equal to 0. Plugging in tau equal to 0 here, taking that out as well, we get minus t plus 1, right? There was another term here which we did not write, which is about the second set of impulses being overlapped. That can be written as, the one in blue can be written as delta tau minus t, that is the impulse situated at t, right, into an impulse of strength minus 1, so I'm taking minus 1 outside, delta t minus 1 d tau. Now this product will be non-zero only at, sorry, this is tau, only at tau equal to 1. So I plug in tau equal to 1 here, take it out. The rest of the thing is 1, we know already. So this becomes delta 1 minus t, or delta minus t plus 1, the same as this. So we get delta minus t plus 1. What was this case? For t equal to 1, this was the case. Moving further, xt minus tau has reached here, where this is t and this is t minus 1. So I can call this condition as t being at, so this was 0, 1, 2. So this is the condition where t is equal to 2. Okay, and as you can see, this is the last possible combination where there will be an overlap, because as this progresses further, as xt minus tau progresses further, there will no longer be an overlap. So there will be no further products, right? So this is the last one. And how can we write this? There's only one overlap, and therefore this is the output. We can also say that for t greater than 2, yt is equal to 0, just like how we wrote earlier for t less than minus 1, yt is equal to 0. Now we've got to sketch the output, right? Let us check. At minus 1, what we had got? We had got an impulse delta minus 1 minus t, which we had concluded it is an impulse situated at minus 1 having a strength minus 1, right? At t equal to 0 is an impulse delta t having strength 1. At t equal to 1, we have an impulse delta minus t plus 1. So let's figure out how does this look. So you had an impulse at 0, then you move it, so you shift it by minus 1, like you shift it to the left side, and then you reflect it. That means you've got an impulse here. Okay, so at t equal to 1, you've got an impulse of strength 1. What about t equal to 2? At t equal to 2, you've got an impulse having strength minus 1. And how does this really look like? So you had an impulse here, then you shifted it by 2 units to the left, and then you reflected it, right? So this is what yt is. And if you had to write this, you could have written this as minus delta 1 minus 1 minus t plus delta t plus delta minus t plus 1 minus delta 2 minus t. If you notice, this is the graph, and this is same as saying that this is as if this was minus delta t plus 1 plus delta t plus delta t minus 1 minus delta t minus 2. Thank you.